Thank you, and well, Merlin, give it 30 minutes before you might want to take back your statement here. And thank you for the opportunity to be here. We're going to shift gears a little bit. It's been some interesting discussion here this morning, and talk about weather and climate. And it's a real pleasure, well, as a self-proclaimed weather geek, to be invited to meet with a group of animal scientists. I think it's the type of thing I think more and more is needed. And I know I've talked to several of you. It's very, very informative, and we see a lot of parallels. But what I want to spend the next half hour or so is talk about is climate change, climate variability and change more appropriately. And in doing so, there's three major pieces to this. We're going to look at some historical trends across the region, some projections for the future, and some of those are probably fairly good, high probability, others less. We'll talk about that. And ultimately some potential impacts and implications for livestock production systems here in the region. Now, I'd also have a disclaimer at this point in time, what I'm not going to talk about, because we would need a whole nother conference, and that's the mitigation part of this. There obviously is a link between climate, especially the climate change, and things like greenhouse gas emissions and so forth. That's for another day or time. What I want to concentrate on here today really is the climate part, the direct front end of this, and maybe at a later time. That's obvious. It's certainly no less importance to this industry, but it's one I'm not going to touch on much today. Well, we'll start off here with a reminder, I guess, more than anything, and that is, as much as we as humans like to think of climate as a static, unchanging, stable entity, it's anything but. And there are a number of natural causes of climate change. There are some that are linked to human activities. But the bottom line is that the Midwestern US climate has varied from tropical 400 odd million years ago, when the North American tectonic plate was closer to the equator than it is now, to glacial and everything in between. So there have been massive swings and changes in the climate long before humans were there. And it just so happens, though, that in the last couple centuries, and maybe longer than that, depending on who you believe, but the human activities are also now influencing the rate at which climate changes. So climate is dynamic. That is by nature. So that's one, I think, take home. It's one I always stress with students. But I want to start with some historical trends and try to make some sense out of lots and lots of data and series from around the region. I'm going to start with a global trend. Thermometers have been around for a couple centuries. And in terms of our instrumental record, we know some things, but essentially we don't have enough measurements or observation series or records around the world until about the mid-19th century. And after that, again, a lot of painstaking work has been done to try and make some sense out of global trends. And what the global trend basically is, if you put all of the best data together, and the thing to look at here, this is, of course, year is on the x-axis here on the horizontal axis. This one starts back in 1881 and goes through 2010. And each one of these individual years is expressed as a difference between the mean annual global temperature that year minus a 100-year normal. So it's sort of a departure from a long-term mean. And what you can see is that, well, the end of the 19th century was basically somewhat cooler than normal. This blue line, by the way, and you're going to see several of these, this is a moving average, about 9 years, and it's used to filter out some of the year-to-year extreme variability, and so we can concentrate more on longer-term, decadal or so type of trends. And what you can see is that, again, relatively cool conditions here for the last couple decades of the 19th century. There was a warming of about a half a degree Celsius the early part of last century. That was followed by a little bit of a cooling trend from around 1940 to the 1970s, and then temperatures increased another half a degree or so. So overall, when you look at this record here, essentially you've got a change, and I knew I was going to try not to hit the mute button, but I did it by accident. Sorry about that. You've got a change of somewhere on the order of a little bit less than 1 degree Celsius in approximately 120 years. Now, you say 1 degree, that's hardly anything. But the point is that there is more to that, and that, from what we know from geologic records and longer-term paleoclimatological studies is that change in temperature, that's actually somewhat significant in terms of global. Remember, we're taking the whole world and adding everything together, and it's actually taking place in a relatively short period of time. So that's a fairly significant change, at least warming globally. Now, not all regions of the world have warmed. Many have, the majority have, but there are some parts of the world that actually have not, and that's important to note as well. So not all parts of the world warm at the same rate. Here in the Midwest, this is it's a couple pieces to this. This one goes back to 1900 up through 2010, and we're looking at the individual years here relative to a 30-year normal, or 30-year mean, 1961 to 1990, and what you can see is a lot of noise. And in the Midwest, we essentially had warming like we did globally from about 1900 up to the 1940s. That was followed by a cooling trend of somewhere on the order of about 0.5 degree Fahrenheit. And that in turn was followed by another period of warming over the last approximately 30 to 35 years. And so overall, the Midwest has become warmer. But the interesting thing, and it's extremely interesting, this is not uniform across seasons or even the time of day. And when you take apart this record here, the temperature record, looking at mean temperatures, most of that warming we just saw has occurred during the winter and during the spring seasons to a little bit lesser extent. And at night. Our minimum temperatures are warming more rapidly than our maximum temperatures. So the diurnal range, the difference between the two, is less than it was before. And this is especially true since 1980. There was a discontinuity in many of our climate records around 1980. The temperature is one of those. So our region has become warmer, but a lot of that has occurred during the cool season. Now if we look at summer, and you can see some of the individual states here I've broken out in the Midwest, we've even seen cooling in some of the Midwestern states. Now here's another one to throw at you. Some of that summertime cooling may be related to the landscape. And that's a landscape covered by either corn or soybeans in many areas. And there is very good evidence, very strong evidence to suggest that some of our agricultural landscapes have resulted in that summertime cooling. The other part of that too is that all of that transpiration from plants, or evapotranspiration more accurately, is increasing the levels of humidity. So humidity is also increasing with time, especially during the last 30 years. So again, if you look at the average annual changes, yes, it's warmer, but you got to take the seasons into account. There have been changes also in the seasonality, very, very important for agriculture. This is a little bit of a mess, this diagram, but this is looking at the change or relative change of the date of the last freezing temperatures of the spring. That's the green, and the days here are on the vertical axis, and the year on the horizontal, and with which that occurs at time. And what you can see if you follow, it's not easy, but if you follow the green line here, the last freezing temperatures of the spring have been progressively getting earlier. The same time, you look here in blue, and that's the relative change of the first freezing temperatures of the fall. And that is occurring relatively later. And so the difference, and that's the red here, is basically your frost-free growing season. That has increased on average by about a week to a week and a half over most parts of the Midwest. So if you want to look at strictly as cropping opportunities, you've got an extra week and a half of growing season. Work we've done in Michigan and for the Great Lakes region, we can say that this is also not symmetrical. More of this, more often than not, is occurring in the spring. So we're getting more of an advance of the spring season than we are in the fall. And I think, again, if you take the mean, it mixes some of that out or averages some of that out. But more of that change is occurring in the spring. This is an example. Most of you remember in the region of our heat wave in March of 2012. Off the charts. We ran out of superlatives to describe March of 2012. It was the largest departure on record for any month in terms of above or below normal. In Michigan, it was almost 14 degrees Fahrenheit above normal. Thousands of records were broken. But if you're a cold-blooded organism, a plant or an insect, basically your life cycle is strongly tied to that seasonality. And this graph here is another research project I'm involved with, looking at risk to tree fruit in Michigan. A lot of fruits grown, as Merlin mentioned here just a second ago. This is the date, and this is expressed in calendar date. Day 70 would be the second week of April. Day 140 would be late in May. that tart cherries reach the so-called side green stage. And the reason we look at that is that's when they become very vulnerable to frost freeze conditions. So it's an important threshold, but it's all temperature driven. And so if it warms up early, these guys come out of their protective dormant states and start up early. And as you look over time at the last 100-odd years for representative site, this one's up in northwestern lower Michigan, you can see that that date is gradually becoming earlier. Note here that this big change occurs right around 1980, that discontinuity I mentioned, and there's 2012. Now, the good news is, at least for this year, when we actually have a fruit crop, we didn't in 2012. This year, it was way back up here, the data with this, so it was much closer back up to the mean. But again, seasonality has shifted. It's starting, in this case, it's suggesting it's starting at least a week and a half earlier spring, the green up, the warm up than it did before. So that's another piece of the seasonality. What about precipitation? Well, there are trends with this as well. Not only has the Midwest become warmer, and I know somebody's going to say, well, what about the drought last year? Well, just bear with. Even with the drought last year, the Midwest is becoming wetter. And again, there certainly are some extremes in here. But it started, this trend towards wetter conditions started way back in the Dust Bowl days in the 1930s. That's the benchmark driest decade on our record. And that's true across most of Central North America, but you can see it here. This is from Michigan. It's representative, though, very representative of the region. And you can see that ever since, precipitation has increased steadily. There have been a couple of blips downward, but overall, we have now on average 10 to 15% more annual precipitation than we did 50 years ago. That translates, depending on location, 4 to 5 inches of extra water. That's important, certainly important for agriculture. And in contrast to the temperatures, which were not uniform, this increase is much more uniform, certainly during the summer. It's also occurring during the winter as well. Now, there are two ways that you can get more annual precipitation. One of them is to have more wet days, just more days with precipitation. That's occurring, no question. This is a chart, and again, a representative site. This one's in East Central Michigan. This is the ratio of days with measurable precipitation at this particular site, and this is very representative. And you can see that back in the 1930s, if you read this, about 1 out of 4 days had measurable precipitation. That value now is more than 1 out of 3. So we just have more wet days. Now, we don't have good data to support this, but we also have more cloudy days. More clouds now than we did in decades past. The green line up here is the events, wet days, which follow wet days, so multiple wet day events. Both of those are increasing and much larger than they have been in the past. So that's one part of that increase. The other part is we're getting more extreme events. So both of those are true and contribute to that increase in precipitation. The graph over here, or the figure here over on the right, these red dots are trends. Red is positive, blues are negative. If you take the sum of the top 10 wettest days each year and look at that trend line, what does that do? And you can see that the vast majority of our region here, we have positive. So the extreme events, 1, 2, 3 inch events, that number is also increasing. So both of those things are definitely happening. Snowfall. Well, this is an interesting one. There are a couple different things going on here. Actually, I can use a crowd participation exercise here. We've got two different charts. This is total seasonal snowfall from the period 1961 to 1990 here on the left. And this is the current normal, 1981 to 2010. So in other words, it shifted 20 years in the future. There are some subtle but important differences. Anybody see? There's two of them, two major ones. Anybody see the differences in terms of seasonal snowfall between these two? One's sort of difficult to see, but it's definitely relevant I know for a lot of folks here. One of them is that the snowfall that we typically have in the Ohio Valley in areas in the southern and central part of the region, that is decreasing. It's either steady or it's fallen a little bit. And that's why you see a little bit northward jog of some of these same lines. So that's one of the changes. So snowfall from large areas of low pressure, synoptic weather systems, the synoptic weather systems are still there, but more of that precipitation is falling in liquid form, going back to the temperatures, which are warmer. So those things, these are all linked together. The other change here is up in our part of the world, lake effect snowfall is increasing. And you should say, well, wait a minute, you just said that winters are getting milder. Why are we having more lake effect snow? And the answer is, it's because we have a lot less ice on the lakes than we used to. with open water. There's all that moisture source, and it's actually showing up again as more lake effect snowfall. So a couple different trends, a little bit more complicated to look at snow. And even in the areas that we have more snowfall than we have in the past, the number of days with snow cover on the ground is decreasing because it's melting more quickly. And that shows up, this is a trace, this is from a site up in the central UP, but again, in one of those lake effect areas. So very, very interesting, but all of these things point to milder winters, almost without exception. I mentioned moisture. What happens to that extra 4 to 5 inches of annual precipitation? I had a student that just finished up his master's program, and he was looking at the climatology of soil moisture. That's a really exciting topic, I know, for you think about this, but some very interesting trends across the upper Midwest and the Great Lakes. This is it's an interesting diagram, very colorful, but once again here we have that calendar day variable on the vertical axis. Day 100 would be late April, day 350 would be, of course, late in December. So we're going from earlier to later in the year here, and we have year on the vertical or the horizontal axis, sorry, and then what we're looking at here is the frequency at which soil moisture in the top 5 feet, 1.5 meters of the soil profile, falls below a value of 0.5. Well, what does that mean? Well, that's the point at which most plants begin to start to have some problems extracting moisture from soil. It's sort of a metric of quasi-index for the beginning or onset of stress. So the more frequently that happens, the less water the plant has available, and of course for agriculture that's a huge deal. And what you're looking at here in terms of colors is the relative frequency which this happens and when during the year. And what you can see with these colors is, not surprisingly, you see the seasonal drawdown in moisture starts here, and this frequency of this condition is maximum, not surprisingly, late July through August into the beginning of September. That's what we know. That's when we had the lowest soil moisture during the course of the year. The interesting thing, though, you can also see some periods like the teens at this particular site. Here are the Dust Bowl years of the 30s and the 1950s, is areas or times in our past that were relatively drier. Note, though, there are a couple of changes. One is the frequency with which this happens is decreasing with time, and that's a direct result of the increasing precip. We've tied those two together. The other one that we didn't know about was that the date at which this occurs is getting earlier, and that follows what we said about the changing seasons. The spring warm-up is occurring earlier. We're using water earlier. So all these things, you can see dynamic links between all of them. And we've taken this a step further with crop simulation models. And here we're looking at if we hold everything constant except climate or weather. And we put it into a crop simulation model, in this case for corn, in the central corn belt of the eastern upper peninsula. Just looking at the sort of, if it sounds funny, it sort of is, but it was with a project looking at in the long-term future. But without question, and this impacts certainly the livestock industry, we have seen major gains in productivity in northern parts of our region in terms of forage productivity, without question. And some of it, a great deal of it, the majority probably, is due to technology, but some of it is due to improved weather. That's an important climate. That's also happening. Well, let's look ahead. What do projections of the future say? Most of these come from very, very comprehensive, dynamic computer simulations, making assumptions about the future, and some of those are good, some of those are not so good. But collectively what they say globally is that depending on how much greenhouse gas emissions occur in the future and the rate at which those occur, that overall the world is going to warm between 1 and 4 degrees Celsius by the end of the century. That's essentially the bottom line. Now, it doesn't seem like much, but again, in this time frame, what we know geologically is that's a very, very rapid change. And these scenarios are definitely, the projections are correlated with how much greenhouse gas emissions and how much efficiency there is in energy and so forth. But right now, we're working with a range of 1 to 4 degrees. There's going to be a new estimate of this coming out within the next year, the IPCC 5th assessment. Right now, it looks as though there are not going to be many changes from this is from the 4th assessment, but probably not too many changes. So globally, all these things suggest the planet warms, or the globe warms on average. For the Midwest, what that means, and we have two time frames here, one for the mid-century with both a high emission scenario and a low greenhouse gas emission scenario here on the left, And then the same thing for the end of the century, 2080 through 2099. The Midwest actually is projected to warm a little bit more than the global average, somewhere between 3 and 6 degrees. You can see the greatest warming for all of these really is up in the upper Midwest, and it's in areas geographically away from oceans because land masses can warm up more than areas adjacent to the oceans. So collectively they suggest big changes. At least that's what the projections say. And this is an oversimplification of something very complicated, but I put it here because when you ask somebody, well, if it warms 4 degrees Celsius, what does that mean? What's that like? Or what does that mean? And if you took Michigan and you warmed the climate, as we've just seen, at least the projections suggest here, basically Michigan's climate in the future becomes like the mid-Mississippi Valley by the middle of it, or even further south by the end of the century. That people grasp, and I think I really have trouble sometimes including this. I think it's an oversimplification of something that's really, really complicated, but it does give you some idea, at least to illustrate representative, or how far would one have to go to find a climate that much warmer. And that is significant. Of course, things work differently in that part of the world than they do in the upper Midwest. So it is a major change. For the livestock industry, one variable of particular importance is apparent temperature. Now, I look for the temperature humidity index, which much of the livestock industry has used for many years as a metric looking at livestock heat stress, and couldn't find a study, but I did find one from a friend in Illinois who's looked at apparent temperature, and this is very, very similar. So this apparent temperature that's listed here and THI are very, very similar, and it's based on the premise that as temperatures go up, the air can hold more water vapor. And of course, with more water vapor, or with a higher humidity, mammals, certainly livestock that are sweating or trying to lose heat or dissipate heat through evaporation, it's basically not as efficient. And it doesn't take place as rapidly. So apparent temperature, much better way of looking at this. And all of the projections we have suggest that, in this case, the maximum daily apparent temperature will increase with time. So what this means with, well, no other way of looking at it, it basically means a greater threat of heat stress for animals. That's the bottom line. And I should note at this point in time that while we're going to look at precipitation next, and precipitation, there's not agreement between all of these. There are roughly a couple dozen groups around the world that run these large comprehensive simulations. They take days and months of computer time to run. They're very expensive. They're complicated to do. All of them suggest warming. There are no exceptions, any way you cut it. Precipitation, though, is different. And with precipitation, I think it's important to note here, we've got this by season. If we look at the Midwest and we look at relative changes in precipitation this century, they basically suggest that in some parts of our region we might see greater annual precipitation. There's an important caveat on that. Some parts of our region, especially as you go south and west, out into the Great Plains and south, there it's a different story. There the annual precipitation is projected, and by most of those models, these are certainly not unanimity like what we saw for temperature. These hashed lines here mean that at least, I think, 70% of the models are in agreement on the direction. But the most important thing, I think, that message here is that most of these models suggest that even if there are increases in precip, they occur during the cold season. Winter, and followed to a little bit lesser extent by spring, but look at summer. This is a big, big red flag for all of agriculture because, of course, our water needs are typically greatest in the warm season, and most of these projections, and there's not a consensus here in most of them, but many of the projections suggest that summers will be drier. And that's something that now with the new ensemble of new model, we're looking at very, very carefully with the new but again, not too many differences yet. So one of the outcomes, or one of the suggestions here is, and it seems like it's almost counterintuitive or an oxymoron. Some of these people say, well, we're going to have more precipitation, but we're going to have more droughts. You think about that in a second. Well, how is that possible? And there's one way it could happen. It's an important link, and that way is that, yes, we may have more annual precipitation, but the rates at which it occurs, the frequency with which it occurs changes. And ultimately, what some of these projections suggest is that precipitation, even though it might be heavier in some cases, it becomes more erratic. And that's also a major problem, because for agricultural systems, it's not just the amount, it's the frequency. It can be just as important as how much. So that's another thing we're looking at, although there's much less consensus about this. That's a relatively low confidence compared to things like heat stress. Those are much higher probability of occurring. And that leads into another point here, and a very, very important one that's often overlooked, and that is that what we've seen here mainly are changes or bulk changes in mean state. Yes, 2-3 degree warming over a 70 or 80 year period. Okay, we can deal with that. And I'm sure most of the people in this room, myself included, would say if the agricultural industry has time and they have a fairly good projection of where we're headed, they're going to be able to engineer a solution. Technology can deal with many of these things. We either change varieties of what we produce, maybe we change different crops or livestock types. But the point is that history, there's a very strong, I think Bill or someone mentioned this morning, there's a very strong track record by the ag industry. That's certainly a reason for optimism. But those are changes, again, predictable changes in that mean state. If there are changes in extreme events or variability, this is a much different story. And it's one, unfortunately, which relatively little is known about. What happens to extreme events? What happens to the frequency of droughts, hurricanes, hailstorms, etc.? If those change, it becomes much more difficult to try and engineer a fix too. So we need to make the distinction between these two things, between mean changes and changes in variability. Historically, one thing about that, we do know that the number of many types of extreme events, especially precipitation, heavy precip events, that is increasing. This is an index for the upper Midwest. Here, another time series, and it shows basically the green line here that the relative number of extreme events has been increasing for the last several decades. Most of this, again, is due to heavy precip events. One more idea about these extreme events, and that is, I mentioned there's some uncertainty here, and there's a big question about the future, and that is, if we look at the distribution of a particular weather variable, let's just use temperature, that's the most easy one to use. So this is a distribution of our temperature. As it changes, and we know climate changes, and if it changes like it's projected, what we don't know is what happens to the shape of that distribution as it is shifted. Is it just a phase shift where you pick up the whole distribution and move it up a couple degrees? That would be very, very easy to deal with statistically and in terms of engineering. Or do we have something like this down here at the bottom? Do we have both changes in the mean state and variability? Very, very different problems. And this one, again, the issue is it's much more difficult to try and engineer a fix or to adapt, if you will, or cope with changes like you see here. And the problem is, again, this is one of the least developed areas of climate change research. There's a lot of work going on in this, but those model projections, unfortunately, they just do not do well with these extreme events. They can't, the scale, both time and space, there's a mismatch. And so we don't know. But I will say one thing, from statistics and from our history from the last few decades, we know this is a record high and low temperatures on a daily basis. What we're seeing observationally looks more like this, at least for the last few decades. And I've been involved in a research project as well, looking into the future, and even the future changes looked a little bit like this too, where the shape of the distribution was similar, it's just that we shifted it in a different direction. So stay tuned on that one, but it's a very, very important one for all of us. One last thing too, the media, we hear a lot about weather disasters and extreme events, and if we look at worldwide weather disasters, I think these are multi-billion-dollar losses. Back to 1980 through 2010, unmistakably the number of those disasters is increasing. And there's a valid point here. So the only way that you can get an increase here, again, is either the numbers of those events are increasing with time. And for some types of events, most of these are tropical cyclones / hurricanes. That's a big one. But droughts are also in here. Droughts are huge in terms of economic impact. Either those are increasing or something else is increasing. And there's been at least a couple studies that have looked at this from the insurance industry. You can imagine they're pretty interested in this. And basically the consensus is, the message is that in some cases, yes, we have seen an increase in the number of extreme events, but what's really changing is there's more stuff in the way. The vulnerability is changing. And that's something, I guess, I throw back to you to look at your operations and how things work. It's something we all have to think about because it's a very, very important part of learning or understanding the impacts that climate has on our day-to-day operations. So it's not sometimes as straightforward. A lot of times the media runs with this and just saying, oh, we're seeing more tornadoes. That's not the case. Some of these things, some have even been decreasing, but again, there's more stuff in the way. A couple things about impacts. In terms of overall for agriculture, one take home, if you take the literature for the last 10 to 20 years in terms of climate change impact, and you look at all of the studies that have been done around the world, there's a couple messages. And one of them one is that there are winners and losers with all of these. If you shift the weather and climate, you're going to make changes, and again, depending on your location, some of them are going to probably be negative, but some might be positive. And if you collectively look at that over the whole world, what most of the literature suggests is that most of the losers are in low latitude areas, the tropical and subtropical parts of the world. There are actually some potential gainers in the mid and high latitudes. I mentioned here both Russia and Canada, which have the largest high latitude land masses in the world. And, well, if I were more accurate, part of the northern US should be in here as well, at least on paper and from what we can tell. There are many, many questions about this, but this is an important thing. It comes into a point here in a little bit. Now, in terms of livestock, specifically in livestock production systems, there are a couple of direct impacts I'm sure most of you have thought about, but changing, especially temperatures, warming temperatures are going to result in changes in heat reduction and generation needs for a system. And so this is a give and take. I think like Lee, it was mentioned this morning. It's a balance, and this is certainly one. So yes, we may have more heat stress during the summer, but we probably will have less cold stress in the winter. So there's a balance. I'll talk more about that in just a second. There are issues with nighttime recovery. Some of the minimum temperatures coming up, there will be less time, and that could become more of an issue than it has been in the past. We have, well, I'll call it still direct, but it's somewhat indirect. We've got to look at our feed system. Where's that coming from? I'm going to mention this in just a second. With a longer growing season, with more carbon dioxide, we have at least the potential opportunity to produce more forage. But with more CO2, we do know one thing, that it typically has lower protein content than forage produced at a lower CO2 content and a lower digestibility. It also doesn't account for things like the pest complex. Huge wild card. Not much is known about this. Some other, going down the list here, changes in heating costs, cooling needs, infrastructure changes are probably going to be an issue. I mentioned the pest complex. That's one that, again, there will be some pluses, some negatives with this. But the bottom line is it's a change. And any kind of change in our system, whether it's positive or negative, means you probably have to respond to it as an operator. One other one that's come up here recently, and that's, we heard this, Ryan talked about this morning, Ron talked about this. We're dealing with systems that have been finely tuned based on cutting-edge research to make the system as most efficient as possible. It's up at a high level of productivity. A couple of recent studies suggest that those types of systems are relatively more vulnerable to these external changes, or hopefully their changes are not shocks to the system. That's something to think about too. So sometimes, I guess another way of looking at this, sometimes simplicity is a good thing. But that's just basically, again, looking at vulnerability. Finally, something my colleague Wendy Powers refers to as resource competition. If we step back and look at this holistically, and we do have these external changes, we've got to think about how our system operates. This is looking for things like competition for water, for forage materials. Ethanol would certainly be in this part, and above all, it's an international market. It's an international system, and changes in other parts of the world might not affect us tomorrow or next year, but they may a couple decades down the road. And so this is a catch-all, but it's a larger type of issue. This is also in the proceedings, some results from a landmark study in terms of impacts, climate change impacts on animal ag systems from Frank et al. And this is representative, I think. They looked at this for swine, for beef cattle, and for dairy systems. And the results were very similar for all of them. And there were regional differences. That's one of the points here. There were two different climate projections that were used. The one on the top here in the bold, that's the CGC, that's the US climate model system. Relatively larger changes, warmer temperatures. The one on the bottom is from Europe, from the UK Met Office. And you can see here, these are changes actually in weight gain for the middle of this century versus historical change. And what most of these things suggested, they also went through the end of the century, they basically suggested changes in productivity on the order of several percent, typically 3, 4 to as many as 10%. For all three of those types of systems, it was greater for the late century. Another interesting thing is here that most of the changes, well, most of the negative changes occurred in the southern US, where they're already relatively warmer right now. There were some positive changes up here in the upper Midwest, and the authors also noted that there's a seasonality issue, that losses in the summertime were offset, at least partially, by gains in the cold season. And so those themes seem to repeat themselves in the literature that's been done. And overall, I would also note that climate change impact, the science here, looking at impacts for livestock production systems, I think it's less developed than it is for plant-based agricultural systems. And it may be because of the complexity, I don't know, but there's still a lot of questions to be answered here, I think, for animal systems. I mentioned feed and forage availability. This is from some other research I deal with, but one is that for the upper Midwest, again, there is, at least on paper, there is positive potential here. And this particular series, this is looking at a projected yields, in this case wheat. This would be the same for soy. It wouldn't be different. Those are both C3 plants that can take advantage of the extra carbon dioxide. For corn, it's not quite as much, but there is a significant potential increase, at least for the next several decades, in much of the upper Midwest. That's something we need to think about in light of this, one of the last points. I apologize for this. It's from, basically, this was published 2 weeks ago, and it's really difficult to see. But this is some results from a study done by Deepak Ray and colleagues at the University of Minnesota. And it's very interesting and it's somewhat compelling. This is looking at recent changes in crop productivity for 4 major food crops: corn, rice, wheat, and soy here across the globe, major production areas. This is looking just basically at actual production. And the really compelling thing about this is that in many parts of the world, especially across parts of South and East Asia and in parts of Africa, but it's even areas that have been traditionally very productive, production is either leveled off or is even declining. That should be, and this morning Bill very well pointed out, 70% increase in food needs by the middle of this century. Where is that going to come from? Well, we're doing our part. The U.S. and North America, it's still increasing. Actually, it's increasing much larger than the average rate. But there are many areas of the world, notably India, also in China, where yields have leveled off or declining. What that means for the livestock industry, though, again, looking at the bigger picture, is it's where are these foodstuff or feedstuff resources going to come from? And it's going to get more complicated with time, probably, if, again, the projections, these projections are accurate. So, summarizing here again, we've gone over lots of things very, very quickly, but the Midwest has become warmer and wetter, especially during the last few decades. Projections, now it's interesting to note that most of our projections also suggest warmer and wetter in the future, but they're big caveats with that. Maybe drier summers. Collectively here, it's another reason it may be more than coincidence. And again, the projections are just that. They're the best educated guess we have, but there's a lot of agreement between them. And I think that's something we need to take seriously. Some types of variability here might, like drought, maybe increase in the future. There's a lot less confidence about this. This is a big wild card. It's a huge wild card. The other part of this is, I didn't mention it, but you look at the overall number of impacts on human systems, and extreme events are associated with a big chunk of it. It's really, really important. A lot more research is done there, is needed there. And finally, impacts for the livestock industry here. You can see those listed, but a lot of it has to do with changes in temperature. But there are also, we have to look internationally as well. And with that, I will finish up on the shore of Lake Michigan here. Thank you. Oops.